Hello everyone, welcome back to Chem Story. Today, we're diving into a concept called VSEPR theory that stands for valence shell electron pair repulsion. I know the name sounds a little long, but the idea behind it is actually really straightforward. Since all electron pairs carry a negative charge, they naturally push away from each other. And because of that, they try to spread out as far as possible to minimize that repulsion. This simple rule helps us predict what shape a molecule will take just by looking at how the electron pairs are arranged around the central atom. VSEPR theory helps us understand why molecules take on certain shapes instead of just randomly floating around. The main idea is pretty simple. Electron pairs around a central atom don't like being too close to each other. Since they all carry negative charges, they naturally repel one another and try to spread out as far as possible. Take beryllium chloride, BeCl2, for example. The central atom, beryllium, is bonded to two chlorine atoms, so there are two bonding electron pairs. To keep repulsion at a minimum, these two pairs push away from each other and end up on opposite sides. That gives the molecule a linear shape with a bond angle of 180 degrees. And this same logic applies to lots of other molecules too. Once we know how many electron pairs are around the central atom, we can start predicting what the molecule's shape will be. Now, let's take a closer look at the types of electron pairs. First, we have shared electron pairs, also known as bonding pairs. These are the electrons that are actually involved in covalent bonds between atoms. They're the ones holding the atoms together in a molecule, forming those familiar single, double, or triple bonds. On the other hand, we also have unshared electron pairs, or what we call non-bonding pairs. These electrons stay on the central atom and don't take part in bonding. They're not shared between atoms. Instead, they just kind of sit there, taking up space and affecting the shape of the molecule. One important thing to keep in mind is that non-bonding electron pairs actually take up more space than bonding pairs. That's because bonding pairs are shared between two atoms, so they're pulled in tighter, closer to the bond axis, but non-bonding pairs, they're only linked to the central atom, so they tend to spread out more. And because of that, these lone pairs can really affect the shape of a molecule, especially when it comes to bond angles. They push the bonding pairs closer together, which makes the angles smaller than what we'd expect based on ideal geometry. Now, let's take a closer look at how different molecular shapes form. And it all comes down to the steric number. That's just the total number of atoms bonded to the central atom, plus any lone pairs around it. If the steric number is 2, that means we've got 2 bonded atoms and no lone pairs. And since those atoms want to get as far away from each other as possible, the molecule ends up in a linear shape with a bond angle of 180 degrees. A good example would be beryllium chloride, or carbon dioxide. Now, when the steric number is 3, things get a little more interesting. If all 3 positions are filled with bonded atoms, the molecule takes on a trigonal planar shape with bond angles of about 120 degrees. You'll see this in molecules like boron trifluoride, BF3, or sulfur trioxide, SO3. But if one of those spots is taken up by a lone pair instead of a bonded atom, the shape changes. Lone pairs push a little harder than bonding pairs, so the molecule bends just a bit, and that makes the bond angle slightly less than 120 degrees. A classic example of that is sulfur dioxide, SO2. Now, when the steric number is 4, we start to see even more variety in shapes. If all 4 positions around the central atom are filled with bonded atoms, the molecule takes on a tetrahedral shape with bond angles of about 109.5 degrees. A classic example of this is methane, CH4. But if one of those positions is taken up by a lone pair, things shift. Now the molecule becomes trigonal pyramidal, and the lone pair pushes the bonded atoms a little closer together. That drops the bond angle to around 107 degrees, like we see in ammonia, NH3. And if there are 2 lone pairs, now we've got a bent shape because those lone pairs are taking up even more space. This brings the bond angle down even further, to about 104.5 degrees, like in water, H2O. When the steric number jumps to 5, things definitely get more complex, because now we're dealing with sp³d hybridization. If all 5 positions are filled with bonded atoms, the molecule takes on a trigonal bipyramidal shape with bond angles of 90 degrees, 120 degrees, and 180 degrees. A good example here is phosphorus pentachloride, PCl5. But if one of those 5 spots is taken up by a lone pair, the shape shifts into a seesaw. That's what we see in sulfur tetrafluoride, SF4. The lone pair throws off the symmetry because it creates uneven repulsion, and that's what gives the molecule its seesaw structure. Now, if there are 2 lone pairs, the shape becomes T-shaped with bond angles of 90 and 180 degrees, like we see in chlorine trifluoride, ClF3. And if there are 3 lone pairs, only 2 bonded atoms are left, so the molecule goes back to a linear shape, just like what we saw with steric number 2. A great example of this is xenon difluoride, XEF2, which has a bond angle of 180 degrees. Finally, when the steric number hits 6, we're working with sp³d² hybridization. If all 6 positions around the central atom are filled with bonded atoms, the molecule takes on an octahedral shape with bond angles of 90 and 180 degrees. A classic example of this is sulfur hexafluoride, SF6. But if one of those 6 positions is taken by a lone pair, the shape shifts to square pyramidal, like we see in bromine pentafluoride, BRF5. The lone pair pushes a little, so the bond angles are just a bit less than 90 degrees. And if there are 2 lone pairs, the molecule flattens out into a square planar shape with bond angles of 90 and 180 degrees, just like in xenon tetrafluoride, XEF4. So as you can see, once you understand VSEPR theory, you've got a really powerful way to predict the shape of a molecule just by knowing the steric number and how many lone pairs are involved. That's it for today's lesson. If you have any questions, feel free to ask, and thanks for listening.